So this is problem 2321, maximum score of spliced array. Let's start with the problem. We got two inputs, nums1, nums2, both have the same length, they are an array, and then we can do this operation where we can swap contiguous subarray subsequences of the array with the same uh, the same index. Okay, so you see this left and right both are the same, and then we can swap that value, and we can do this operation once or not doing it at all. And then we need to find the maximum possible score. What is a score? A score is the maximum value of some nums1 or some nums2. So what this swap doing is actually to manipulate the value of nums1 or nums2 and then find the better score out of it. And score is the maximum sum from either nums1 or nums2. So maximum possible score is basically the maximum of the maximum sum between nums1 or some nums2 when we can manipulate the value of nums1 and nums2 by doing that swap. That's the problem. Let's see an example. So we have this nums1 and nums2, and we know that to make this maximum, we swap the second digit here. We swap that second numbers, and this becomes 60, 90, 60, which is 210, the maximum value, and we return that maximum score, 210. Well, for this one, to make it a maximum score, we swap this last two digit, and then this one become the maximum. Okay, and that is 220, and that's what we return. So that is the problem. Let's see first the constraint actually before we go into the tactic. We can see that all numbers in the array are positive. Okay, so then let's start with the tactics. Let's take this as an examples. So for the tactics, the brute force way obviously to try all permutation. How to try all permutation? We can think of it by trying when we change only one numbers, what will be the maximum? Then when we change two numbers, what is the maximum? Then when we change three numbers, what is the maximum, and so on and so forth. But obviously that is pretty expensive, right? Now, because anything brute force means we are not optimizing it yet. Let's think about how can we optimize this. The way we can see one potential starting point is actually to see the fact that when we try to look at this swap and then find the maximum, then when we try to look at this one, when we trying two numbers, and then when we trying three numbers, there is an overlap there, overlap of the digit that we are looking for. So that is a potential, but we don't see yet what is actually the properties of that overlapping that we can leverage. But we can see an overlap there, right? The 3 is having a subpart of the 2, having a subpart of the 1, while the 2 is having the subpart of the 1. The 4 having the subpart of the 3 and the 2 and the 1. So it sounds like a good starting point. Now let's explore it and find the idea while we are exploring it. So how to explore this? We need to picture it back to the initial problem context. What is the problem context? It's about finding the maximum score, and max score is the maximum of the sum. Okay, so knowing that, let's see it one by one. Let's make it looks like nums2. Let's treat nums2 as a candidate winner. So when nums2 are as candidate winner, how do we know all this swapping going to affect the nums2 value? Is basically by looking that for each swap, what it means is nums2 lose its original value and get the value from nums1. So treating nums2 as candidate winner first, we know that for each step just now, what happened is it will lose value, it will get value from nums2. So let's see when we took only the first digit here to be swapped. What it means here, actually, nums2, the changes to nums2 is nums2 will get the value from nums1, which is 20, but it will lose the value that it initially held, 50. So what happened when we swap the first digit, what happened to nums2 is actually it will lose 30 points. Okay? Now, what happened when we include the second digit? So what happened here is it will get value from nums1, which is 20 plus 40 is 60, but it will lose 50 plus 20, which is 70. So what happened is nums2 going to have a reduction of score by minus 10. But look at here. This is much better than this one, right? So what it's indicating, it means that there is another potential when we are including the second number to have a better value than minus 10. Why? Because we know the first digit actually making it worse, minus 30. And when minus 10, which is better one, it means that the second number actually doing something good here. The second swap is actually doing something good. So actually there is another potential that is including the second digit that make this better. And what it is? It is actually by removing the first digit involvement. And how to remove it? It's simply by eliminating it. And we know the first digit involvement actually contributing of minus 30. So in the end, minus 10, eliminating the first digit involvement, it's become minus 10 plus 30. So it's become plus 20. So when we include the second digit, in actuality, we can get a maximum of plus 20 by ignoring the first digit. So we only swap in action, actually, it means we only swap the second digit. That's what this means. So you see here, when we track down these numbers, we know a better version that is potential when we include the new digit what we consider. So let's go further and see how this actually helps when we explore it deeper. Now let's take the third digit. When we take the third digit, it means 60 plus 20, 80. We will get 80 from nums1 and we will lose, this is the 3 digit, right? 70 plus 50, it means 120. And this will be 1 minus 40. Out of the previous values, this is worse. This is the worst. So it means there is nothing much more better that we can create out of this new digit involvement. Because this minus 40, which makes it is the worst one, meaning that the third digit actually really bad. So there is no way by eliminating the previous one we can get anything better, because this is the worst. Okay, this is the worst. So even if we try to get eliminating this and this, that wouldn't be much helpful, because the new digit doesn't give us better things. Okay, it's different when the new digit giving us a better things. Okay, so that's when we know we don't need to take care of it. And then when we go to the next digit, the fourth digit, when we go for the fourth digit, it means we get from the nums1 80 plus 70 is 150. This one will be 120 plus 40, 160. This is, wait, is it true? 120 plus 40, 160. This one 80 plus 70, 150. Okay, so we will get minus 10. And minus 10 here, we know that it can be better because what? We know that the worst was minus 40, right? The worst now no longer the minus 30 but minus 40. It means we need to eliminate the involvement from here and here. So the maximum we can get out of that minus 40 removal is actually plus 30. What it essentially means is because minus 40 is this one, change that involve the first three digits, it means that we essentially only swap the fourth digit. Okay? And then the last one. So this will be the last number. So 150 plus 30. We got from nums1 180. We lost from nums2 160 plus 20 180. So in total, if we include everything, we got 0 change. But we know that this can be much better by eliminating the worst component. The worst component is this minus 40, which is including the first three digits. So in total, we can get plus 40. Okay, so if you see here, we can get all possible things that can be happening to the nums2 with the concept of getting it into maximum nums2 by going only through here and remembering what was the worst. And this becomes only big O n because we only need to traverse here. Compare it with the permutation that is the brute force doing. This is much more efficient. But we need to remember here, although in this case it's true that nums2 is the candidate, but the true candidate and become the true winner. It's not always the case. So what happened when we write the algorithm, we need to also do the same thing, which is treating nums1 as the candidate of winner and then considering the changes that can be happening to nums1 and then compare the two results and find the maximum of the maximum. Okay, so that is about the tactic, and that's how we can make this into only big O n compared to the permutation solution in the brute force. And to summarize the idea how we can get into this optimization is by understanding the overlapping first. After understanding the overlapping, we actually explore it one by one, the overlapping case, and then put it into context into the problem. What is the context of the problem? It's actually to maximizing after we swapping, right? So for each swap, we track down the changes possible, and then when we go into the second change, we understand a bit, we got more idea of what can be a potential candidate of optimization, which is leveraging the values of this whenever it is actually lower than what we found here. And then we understand from the third one that what we need is to track is actually simply just what was the worst that we already explored. We only need to memorize that and use that words to actually find the maximum potential for each new digit involvement. Okay, so that's about the tactic. Let's write down the code. So for the code itself, we know that everything will have the same length. So to make it just nicer, let's write it like this. N is length nums1 because nums1 and nums2 have the same length. Okay, and then we know that we need to track down the changes value. Okay, so change value, let's say change2. Let's just start from what we write first, okay, to make it simple translation. Change2 is an array, okay, and then this will have the same length, right? Yeah, because we track down one by one. so it will be n. Okay, and then we will do the exploration one by one. So for I in range of 0 to n, what we will do is we will do the swap. The swap will include the change to I is basically nums1 I. We get value from nums1, we lost the existing value from nums2. Okay, so that's what this is about. And then when we go to the next iterations, we basically also do it, but we need to include the whole value, so not only the nums1. It means 60 is 20 plus 40, right? 70 is 50 plus 20, but we can get it from the previous one. So basically change to I minus 1. That is the total change we can get. That is how we can get minus 10. But this will impose problem when we actually just starting with the 0, right? Because there is no index -1. So another one way to do this is to do if else, of course. Another way to actually eliminate the use of if else is actually to lengthen this one. And lengthen this one by 1 numbers. When we lengthen this one by 1 numbers, what it really means is now we can grab it like this. Okay, so by doing this, what happened is we initialize everything from 0. So when we traverse through the n, we start calculating from the I plus 1. So the first ever digit is just for initialization numbers. We don't care. We just make it so that we don't need to do if else condition. And essentially that will make your code a little bit faster, but obviously it's negligible. But that is makes also our writing much simpler. So by adding one number here, this is a technique that I recently learned, we can eliminate if else session. So what happened is we are actually only going to calculate from the I plus 1 to the last digit, but so the very first numbers, the 0 digit for the change to, is just to make it, we don't need to do that if else or for when we catering for the first problem. Because now when we go, for example, I0, the very first calculation, we're starting to calculate the change index 1 and the change 0, of course 0 value, which means we don't need to we only need to care for this, right? Which what we can also achieve if we keep the length n but using if else. But I want to eliminate if else because I also want to familiarize myself with this technique so it becomes second nature to me. So that's a simple, nice thing to do. And then that's what we got up to here. Then we got this one. Remember how to make it optimized. Remember in our tactic discussion, we know that to make it optimized, we need to track one thing, the worst thing, right? So to track the worst, let's have this worst to, let's just say worst, we got it it should be starting from what is it, none? Of course, we've got nothing worse yet. Basically, we got nothing worse yet. But for each of these, we will get this delta, not this delta, this value as the potential worst. Worst is basically the mean value of change to I plus 1 or the worst itself. But the problem is, initially, if we do this, initially it will become none. So we need to do this if worst is not none, else it will be this. Okay, so if we already got the worst value update, we update it at the last, of course, then we need to know if the worst value giving us what is the the best potential is actually when we basically this is when we have the minus 10 minus 30. So we know we need to calculate it if the change to plus 1 actually better than the worst. Like for example, minus 10 better than minus 3, that we know it is like what you call it. It is useful to try to calculate the better one, but this one is not useful to calculate the better one because this is making it worse than before. So only when we do this, we know that we need to check for the better potential. And that will make we need the answer because everything positive anyway, so we can start the answer with 0 rather than none, because we know that the sum will be either 0 or bigger than 0 because all member of n is actually positive. Knowing that, we know that answer, or what you call it, max score. Max score is the maximum of max score itself, or this one minus the worst. Otherwise, max score is just maximum of max score and this one. Okay. So this is when we know the condition was actually can be better. This is when it can't, because worst can be none. We need to check this. So after that, obviously we need to update the words, and that is done. So I think that's about it. We just need to do the same thing, but for change 1. This is considering nums1 as the winner candidate. We just need to swap it. This one we need to be careful because we need to bring over the max score from everybody. Let's put it here to make it clear. All in all, we already looked through everything. We just need to return the max score. Okay, let's try. Okay, it's wrong. Why it's wrong? Oh, right. Because this is the change. The max score should include sum 1, sum 2, sum nums 1, sum nums 2. Because what I calculated here is just the change, right? While the score should be the total. So this is when we consider 2 as the winner. So sum 2 plus this, one sum 2 plus this, then maybe initially we can always do this, sum 1 sum 2 more than 0, and we also need to update here sum 1 because this one considering number 1 as the winner. The worst is also about just about delta, so we don't need to care about it. Let's try again. Now we got the right number. So what was missing just now was about, remember that the score is about the total, not only the change, right? Let's submit this. Let's see if it is performant enough to be accepted. Yes, it is performant enough. So what is the time complexity? Like we can already, I think I already mentioned it before, it's actually big O(n) because we explore one by one, right? We do this twice, but it doesn't matter because when it is a separate sequence, big O(n) in big O notation, it's still big O(n). Do we do any ordering, sorting? No, we don't do. We just do sum. That's also big O(n). So the time complexity will be big O(n). And that's it for this problem. Thank you.